Good day and welcome to Big Bad Tech. I'm Instructor Jim Pytel, and in today's short application exercise, we'll program and test a PLC-based unidirectional motor starter with both a momentary jogging operation and a maintained run state. This lecture is predicated on the assumption the viewer has watched the Commissioning a PLC System featuring the TECO SG2 PLR lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. This aforementioned lecture configured a TECO SG2 PLR, an inexpensive basic PLC, to direct the operation of light industrial 120 volts line to neutral, 208 volts line to line, 60 Hz three-phase AC primary circuit, configured such that the F contactor energizes a squirrel cage induction motor in the forward direction, and the R contactor energizes a squirrel cage induction motor in the reverse direction. The F and R contactors are mechanically interlocked such that they cannot be simultaneously closed. The PLC has been configured with the following field input and output devices: a normally open maintain contact selector switch on input 1, a normally closed momentary contact red push button on input 2, a normally open momentary contact green push button on input 3, a normally open momentary contact yellow push button on input 4, the normally open auxiliary F1 contact of the F contactor on input 5, and the normally open R1 auxiliary contact of the R contactor on input 6. The first 4 field input devices are intended for human-initiated interaction with our system, whereas the auxiliary contacts on inputs 5 and 6 serve as feedback about the status of a particular contactor. Note the maintain contact normally closed e-stop is not a direct input to the PLC, but rather serves as a hardwired bottleneck through which all 6 field input devices immediately downstream of it must negotiate to issue input to the PLC. Wired in this fashion, the hardwired e-stop effectively severs all incoming communication with the outside world without the necessity of resorting to any programmed instructions to do so. Let's now examine the field output devices. Electromechanical relay output Q1 directs the operation of the F contactor coil, hardwired with a normally closed overload contact. Electromechanical relay output Q2 directs the operation of the R contactor coil, also hardwired with the same normally closed overload contact. This hardwired connection between the 2 contactor coils and the normally closed set of overload contacts allows the overload to have the last say as to whether the motor is energized or not, and never surrenders complete authority to the PLC. Wired in this fashion, the normally closed overload serves as a means of directly de-energizing either contactor coil in the event of an overload without the necessity of resorting to any programmed instructions to do so. Electromechanical relay output Q3 directs the operation of a red pilot lamp, and electromechanical relay output Q4 directs the operation of a green pilot lamp. Again, note the maintain contact normally closed e-stop serves as a hardwired bottleneck through which all field output devices immediately downstream of it must negotiate to be energized. Wired in this fashion, the hardwired e-stop directly above stream of all field output devices effectively severs all outgoing communication from the PLC without the necessity of resorting to any programmed instructions to do so. For the purposes of this exercise, we will not be making use of all field input and output devices. However, this base system is configured as such for other exercises that may need this additional functionality. Given this PLC can be quickly programmed and reprogrammed as we see fit without the time-consuming necessity of physically rewiring it, this and the next several labs making use of this system should be relatively quick and painless. Here's the pared down schematic representing all of those field input and output devices and primary elements we'll be making use of today. You will no doubt recall that a through-wire control circuit maintains or remembers the last asserted state because it features a holding, seal-in, or memory circuit. A jogging or inching circuit, in contrast, is one that only momentarily energizes an output without the use of a holding circuit. A jogging circuit could be used to briefly energize the motor for purposes of partial movement of an applied load. Customarily, jogging circuits feature spring-applied electrically released friction brakes to increase the precision of the jogging movement. If you necessitate a review of jogging circuits as implemented using traditional hardwire relay-based ladder logic, you are encouraged to revisit the Motor Starters with Jogging lecture available at the Big Bad Tech channel. Various configurations of jogging circuits exist. However, here's the hardwired equivalent we'll attempt to replicate today using the PLC. I chose this particular jogging circuit for today's activity solely because it's not as easy as one might think to implement using a PLC. You might wish to pause the lecture and review how this hardwired implementation might behave given various combinations of input, particularly when an operator presses and releases run, then presses and releases stop. When an operator presses, briefly holds, then releases jog stop. When an operator presses and releases run, then presses, briefly holds, and releases jog stop. And finally, its response to emergency stops, overload conditions, and occasions when the F contactor is physically forced closed. I say again, pause the lecture and familiarize yourself with the function of this hardwired jogging circuit as implemented using traditional hardwire relay-based ladder logic. Dust the cobwebs off that part of your brain where you stored jogging circuits long ago and get to work. Again, if you need help, please revisit the Motor Starters with Jogging lecture available at the Big Bad Tech channel. Assuming you were up to the task, you should have anticipated the following behavior. When an operator presses and releases run, the motor should start, continue to run, since control relay CR1 and its associated contacts establish a holding circuit. When an operator presses and releases stop, the motor should stop and stay stopped since the holding circuit is broken. When an operator presses, briefly holds, then releases jog stop, the motor should run only when the jog stop button is actively being depressed, and upon release, the motor should stop given the holding circuit has not been established by control relay CR1 and its associated contacts. When an operator presses and releases run, the motor should start and continue to run since control relay CR1 and its associated contacts establish a holding circuit. While in the maintain run state, when an operator presses, briefly holds, and releases jog stop, the motor should continue to run only when the jog stop button is actively being depressed, and upon release, the motor should stop given the holding circuit established by control relay CR1 and its associated contacts has been broken by the normally closed side of the mechanically interlocked jog stop button. Really, the only distinction between the maintain run state and the momentary jog mode is whether or not the control relay CR1 is energized. In the maintain run state, CR1 is energized and establishes the holding circuit. In the momentary jog mode, the normally closed side of the jog stop button ensures CR1 is not energized and breaks or does not establish the holding circuit. At the same time, the normally open side of the jog stop button energizes the F contactor coil directly. The moment the jog stop button is released, the motor stops. Again, the accuracy of the jogging movement can be increased by incorporating a friction brake in our primary circuit. During an emergency stop, this system will stop the motor and break the holding circuit regardless of whatever state it happens to be at the time. The system will only return to operation when the e-stop is reset. Similarly, during an overload, this system will stop the motor and break the holding circuit regardless of whatever state it happens to be in at the time. This system will only return to operation when the overload is cooled and reset. Finally, if the F contactor is physically forced closed, note the primary F contacts will make connection and the motor will start. However, the F contactor coil will not be energized, nor will the holding circuit be established. As such, when a technician stops manually overriding the F contactor, the motor will stop. Ideally, we should be able to replicate the functionality of this hardwired implementation using our PLC-based system. Easy, right? No, but not impossible, as we'll soon demonstrate. If you've been following this playlist in its intended sequence, you're most likely sick, and no doubt tired of hearing about all the wondrous benefits of PLCs, as I am tired of going on and on and on about them. Put your hand on top of the internet and repeat after me. PLCs are flexible, reprogrammable devices that make modifications of a system possible without the time-consuming necessity of physically rewiring it. I too share this belief. However, PLCs are not without their shortcomings and idiosyncrasies, as I intend to demonstrate today. Often these shortcomings and idiosyncrasies necessitate creative thinking and a shift in perspective to circumvent. First obstacle to our task is that the PLC chosen for this exercise, the TECO SG2 PLR, is limited to a maximum of only 3 available contacts and 1 output entry per rung. Given this limitation, we're effectively being asked to stuff a watermelon inside a lemon, given the first rung of our hardwired equivalent contains no less than 6 elements. Our task is somewhat simplified, however, by having the e-stop and overload already being hardwired into this system. However, we're still constrained by the available space. Add to our difficulties that our PLC-based implementation needs to effectively respond to overload conditions using real-world feedback using the F1 auxiliary contact, and the fact that we don't want this system to energize the F contactor coil and establish a holding circuit if the F contactor is ever physically forced closed. One might propose the following program, almost a direct copy of the hardwired implementation, only to have our dreams shattered into so many tiny pieces because it violates the space limitations of the TECO SG2 PLR. Note this implementation requires the use of 4 contact entries, in clear violation of the 4 contact entry limit per rung. This being said, it's close and worthy of our inspection. If this program works as intended, we may be able to chop its arms and legs off, roll it up and stuff it in a small box and stomp the lid closed if we get creative and/or desperate. For the purposes of this exercise, we're going to use the normally closed momentary contact red push button on input 2 as our stop button, the normally open momentary contact green push button on input 3 as our maintain run button, the normally open momentary contact yellow push button on input 4 is our jog stop button, and the normally open F1 auxiliary contact of the F contactor on input 5 as feedback input. Note rung 1 contains a make instruction examining input I2, the normally closed momentary contact red stop push button, a make instruction examining input I3, the normally open momentary contact green run push button, and a break instruction examining input I4, the normally open momentary contact yellow jog stop push button in series with a coil of virtual relay M1. Rung 1 appears almost identical to our hardwired implementation, with a notable exception that virtual relay M1, our stand-in for control relay CR1, is not a real physical entity, but rather a programmed virtual element. Rung 2 is where the PLC program departs from our hardwired implementation out of functional necessity. Rung 2 contains the make instruction examining virtual relay M1 and the make instruction examining input I5, the F1 auxiliary contact, in parallel with the make instruction examining I3 in rung 1. This rung establishes the holding circuit if and only if both the coil of virtual relay M1 is energized and the F1 auxiliary contact confirms the F contactor is actually closed. If either scenario is untrue, either because the system is at rest and someone is forcing the F contactor closed, or while the system is running and an overload event directly de-energizes the F contactor coil, the holding circuit will not be established, or if previously established, will be broken. The third and final implementation of the PLC-based 3-wire motor starter lecture, available at the Big Bad Tech channel, discusses this modification in greater detail if you wish to review it. Rungs 3 and 4 are again almost direct one-for-one translations of our existing hardwired implementation. Either the make instruction examining input I4, the normally open momentary contact yellow jog stop push button, or the make instruction examining virtual relay M1 would serve to energize output Q1, the F contactor coil. Again, you'll note neither the e-stop nor the normally closed overload make an appearance in our program. However, these devices are readily apparent in the hardwire schematic. Wired in this fashion, the e-stop and the normally closed overload would serve to override the PLC program in the event of an emergency overload event. This implementation would work if we used an even slightly more advanced PLC that allowed more contact entries per rung. However, we're stuck using the tools we've got on hand, notably a PLC that allows only 3 contact entries per rung. Given this limitation, we need to modify the circuit ever so slightly to accommodate this restriction. Here's one such attempt at chopping this program into smaller functional blocks, but by no means is it the only method of doing so. You note the use of 2 virtual relays, M1 and M2, and their associated instructions inside this program. The comments inform the reader that virtual relay M1 is used for continuation purposes only, and virtual relay M2 is in charge of the maintained run state. Again, we're going to use the normally closed momentary contact red push button on input 2 as our stop button, the normally open momentary contact green push button on input 3 as our maintain run button, the normally open momentary contact yellow push button on input 4 is our jog stop button, and the normally open auxiliary F1 contact of the F contactor on input 5 as a feedback input. Note rung 1 contains a make instruction examining input I2, the normally closed momentary contact red stop push button, and a make instruction examining I3, the normally open momentary contact green run push button, in series with a coil of virtual relay M1. Virtual relay M1 is essentially a placeholder that says to be continued in later rungs. Rung 2 is our holding circuit, consisting of a make instruction examining input I5, the F1 auxiliary contact, in series with a make instruction examining virtual relay M2. Again, the comments inform the reader that virtual relay M2's function is to check whether or not the maintained run state has been asserted. Since the coil virtual relay M2 hasn't yet appeared in our ladder logic diagram, at first you might think this rung isn't doing anything, and in the deactivated state you'd be correct. However, as we complete our tour of this program, you'll see how this holding circuit check is employed in later rungs. Rung 3 is where the M1 virtual relay extension picks up where it left off. Rung 3 contains a make instruction examining virtual relay M1 and a break instruction examining input I4, the normally open momentary contact yellow jog stop push button, in series with the coil of virtual relay M2. Recall that virtual relay M2 is the maintained run state. Rung 4 contains a make instruction examining input I4, the normally open momentary contact yellow jog stop push button, in series with output Q1, the F contactor coil. Rung 5 is a parallel branch of rung 4. It contains a make instruction examining M2. the virtual relay that governs the maintain run state, in parallel with the make instruction examining input I4 and rung 4 above. Rung 6 and 7 serve as accessory indicator functions. When output Q1 is not asserted, output Q3, the red pilot lamp, is energized. When output Q1 is asserted, output Q4, the green pilot lamp, is energized. In summary, red light means the motor should be stopped, green light means the motor should be running. Again, you'll note that neither the e-stop nor the normally closed overload make an appearance in the program. However, these devices are readily apparent in the hardwired schematic. Wired in this fashion, the e-stop and the normally closed overload serve to override the PLC program in the event of an emergency overload event. Yes, this implementation is not pretty, but you're often forced to make unpretty compromises when subjected to cold, hard reality. Case in point, look at your lazy lab partner. I mean, be honest. Would you ever even acknowledge you know this person outside of school? No, you wouldn't. If I saw them on the side of a highway with a flaming arrow sticking out of their neck and a dog biting them in the crotch, I wouldn't even slow down. If you, however, slow down and walk through this program line by line as would a PLC during several scans, you'll note the reason behind its construction. Virtual Relay M1 is merely the means of continuing rung 1 beyond the permissible limit of 3 contact entries allowed for this particular manufacturer. Virtual Relay M2 in turn dictates whether the maintained run state has been actively asserted. The holding circuit in rung 2 is established if and only if the F contactor actually closes and the maintained run state has been asserted. Really, the business end of the whole program can be found in rungs 4 and 5. Either the momentary contact yellow jog stop push button or the maintain run state can energize the F contactor. The primary difference being that the jog stop is momentary and the maintain run state is preserved as long as the holding circuit is established. When the program is downloaded to the target device and placed into operation, we can observe its behavior and simultaneously monitor the program using a live communications link. Note the two videos are synced up, however there's a noticeable lag in the monitoring utility. As can be expected, when the system is in the deactivated state, the F contactor coil is not energized, the F primary contacts are open, and the motor is off. Output Q1 is not asserted, and the red pilot lamp is on, and the green pilot lamp is off. When the green run push button on input 3 is closed, the F contactor coil is energized, the F primary contacts close, and the motor turns on. You note the coil of Virtual Relay M2 is energized, and when the F1 auxiliary contact confirms that the F contactor is actually closed as directed, the holding circuit is established in rung 2. An operator can now release the run push button. When the stop button on input 2 is open, the holding circuit is broken, the F contactor coil is de-energized, and the F primary contacts open, the motor turns off. The system behaves as anticipated for the maintain run state. Let's now examine its behavior during jogging operation. When the yellow jog stop push button on input 4 is closed and momentarily held closed, the F contactor coil is energized, the F primary contacts close, and the motor turns on. You note the output Q1 is being asserted via the make instruction examining input I4 and rung 4 without the use of the M1 and M2 virtual relays. As soon as an operator releases the yellow jog stop push button, the F contactor coil is de-energized, the F primary contacts open, and the motor turns off. The system behaves as anticipated for momentary jogging operation. A spring-applied electrical release friction brake could be installed in this system to increase the accuracy of the jogging movement. Let's now examine what happens when an operator places it in the maintain run state, and then while in operation presses and momentarily holds the yellow jog stop push button before releasing it. As previously, when the green run push button on input 3 is closed, the F contactor coil is energized, the F primary contacts close, and the motor turns on. You'll note the coil of Virtual Relay M2 is energized, and when the F1 auxiliary contacts confirm the F contactor is actually closed as directed, the holding circuit is established. The operator can release the run push button. While in the maintain run state, when the jog stop push button on input 4 is closed, the brake instruction examining input I4 on rung 3 de-energizes the coil of Virtual Relay M2. However, as long as the operator keeps pressing the yellow jog stop push button, the make instruction examining input I4 on rung 4 keeps output Q1 energized, and the motor continues to spin. Outwardly, nothing has changed. Inwardly, however, the holding circuit has been broken, and the only thing that keeps this motor turning is the operator actively holding the jog stop push button closed. As soon as the operator releases the yellow jog stop push button, the F contactor coil is de-energized, the F primary contacts open, and the motor turns off. In summary, when an operator switches between the maintain run state and the momentary jogging operation on the fly, this program breaks the previously established holding circuit as intended. Note, not all jogging programs exhibit this behavior, as you'll learn in an upcoming challenge exercise. Additionally, note this implementation prevents an operator from establishing the maintain run state while the yellow jog stop push button is being actively depressed. Again, not all jogging programs exhibit this behavior, as you'll learn in an upcoming challenge exercise. Let's now examine the system's behavior during emergency stops and overloads. As previously, when an operator presses and releases the green run push button on input 3, the maintain run state is asserted. While in the maintain run state, opening the e-stop directly depowers both the field input and output devices without reliance upon any programmed instructions to do so. The F contactor coil is de-energized, the F primary contacts open, and the motor turns off. When the e-stop is reset, the system returns to the deactivated start state and does not immediately resume operation. The system seems to correctly respond to an emergency stop condition. Let's now examine this system's response to an overload event. As previously, when an operator presses and releases the green run push button on input 3, the maintain run state is asserted. If during the course of operation an overload event occurs, in this case I'm simulating an overload by manually testing it, the open overload directly depowers the affected field output device without reliance upon any programmed instructions to do so. The F contactor coil is de-energized, the F primary contacts open, and the motor turns off. Note the make instruction in examining input I5, the F1 auxiliary contact in rung 2, informs the program that the F contactor has been forced open by some outside influence and breaks the holding circuit by de-energizing virtual relay M1. Virtual relay M2 follows suit and breaks the holding circuit. As can be expected, when the overload is reclosed with the holding circuit broken, the F contactor coil does not immediately re-energize and the motor remains off. Only when the operator actively makes the decision to return the system to operation by pressing and releasing either the run or jog stop push button would it do so. The system behaves as anticipated for overload conditions. Let's now consider a scenario in which a technician purposely manually overrides the circuit by physically pushing the F contactor closed without the use of the push button station. Warning, do not try this at home. Manually overriding a motor control circuit by physically closing the contactor may not be the wisest of actions for all scenarios, especially for those systems incorporating multiple actuators. In this scenario, it is permissible to manually override this system. When a technician physically pushes the F contactor closed using an insulated tool, the F contactor physically makes connection and the motor starts as can be expected. The make instruction in examining input I5, the now manually closed F1 auxiliary contact, does allow logical continuity in rung 2. However, the make instruction in examining M2, also in rung 2, does not allow logical continuity and the holding circuit is not established. Despite the F contactor being held closed, the F contactor coil is not energized and only the technician's purposeful act of holding the contactor closed allows the motor to operate. As soon as the technician releases the manual override of the F contactor, the return springs open the F contactor primary contacts and the motor turns off. In summary, this particular program operates as expected during a maintain run and momentary jogging operation and can switch from run to jog on the fly. Additionally, it responds appropriately to emergency stops and overloads and will allow a technician to momentarily manually override the F contactor, but does not establish the holding circuit in doing so. Before we wrap this application exercise up and go our separate ways, realize this implementation is but one of the many different types of PLC-based unidirectional jogging circuits that can exhibit subtle and not so subtle differences in behavior. As one such example, consider the seemingly innocuous substitution of the make instruction examining virtual relay M2 and rung 2 in our existing PLC program with a make instruction examining virtual relay M1. At first you might think this substitution inconsequential, but it isn't, and a very conspicuous behavioral change occurs for this modified system. If you're up to the challenge, I encourage you to investigate this modification, observe its dramatic consequences. If you need a hint, compare how our previous system responded when changing between run and jog and vice versa on the fly with this modified program's behavior for the same input scenarios. You should notice a significant change. Additionally, if you wish to keep the jogging magic alive, here's a challenge for those brave or foolish enough to attempt it. As a continuation exercise, invite the viewer to write, simulate, and test a program that would direct the operation of a PLC-based unidirectional jogging circuit that uses the maintain contact selector switch on input 1 as a mode selector. The unidirectional jogging circuit should operate as follows. When the maintain contact selector switch is in the deactivated normally open system, this system is now in the maintain run mode and will establish a holding circuit when the green start push button is pressed. In contrast, when the maintain contact selector switch is in the activated normally open held closed position, the system is in momentary jog mode and will not establish a holding circuit when the green start push button is pressed. The normally closed contact red push button on input 2 will still serve as a stop button, and the normally open momentary contact green push button on input 3 will serve as a start button. A functional program should respond appropriately to emergency stops and overload conditions. Quick programming hint for those intended to rise to this challenge. The electromechanical nature of a field input device has nothing to do with how that input can be instantiated in a PLC program. Get cracking and see if your system works as intended. You'll find this isn't as hard as you might expect, although it does take some thought and effort on your part. Take heart that you never have to rewire this PLC-based system, but rather reprogram it. Alright, that's about it for this quick application exercise. In conclusion, we programmed and tested a PLC-based unidirectional motor starter with both momentary jogging operation and a maintained run state without the time-consuming necessity of physically rewiring the system. In the course of this application exercise, we discussed scenarios in which a program must be reformatted to fit the confines of a particular PLC. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.